Hello, this is Jake Abbott. In this video we're going to be talking about the Jordan form. The Jordan form is related to the Similarity Transformation video. In the end of the Similarity Transformation video, we found that if you have a square matrix A, and that matrix consists of only distinct eigenvalues, meaning eigenvalues of multiplicity 1. So we had, let's say we had some matrix that was a 3 by 3 matrix and it had eigenvalues 1, which is not the same as eigenvalue 2, which is not the same as eigenvalue 3. So we have these distinct eigenvalues of multiplicity 1. We found that this A was similar to some diagonal matrix, lambda, by some similarity transformation, Q inverse Q. And so A is similar to this matrix, and similar matrices have the same eigenvalues as each other, and it sort of means you can think of your operation A represented with respect to a different basis set, which is represented by this Q, and then you can rewrite A as being a diagonal matrix. So we found that if all of the eigenvalues are distinct, then this matrix is diagonalizable, meaning similar to a diagonal matrix. But not all matrices have all distinct eigenvalues. Many matrices don't. And in that case, it's not necessarily similar to a diagonal matrix. But every matrix, any matrix A, whether it has distinct eigenvalues or not distinct eigenvalues, is similar to a Jordan form. And this is this word, Jordan form. So what is a Jordan form? It's a type of matrix that we'll see in just a second here, just like a diagonal matrix is a type of matrix. So let's begin by assuming that we have a 3 by 3 matrix. We're going to sort of learn by example here. So A is this 3 by 3 matrix with an eigenvalue lambda of multiplicity 3. Multiplicity 3. So I have basically only one eigenvalue. I mean, it's like, what if it were lambda was 5? So my three eigenvalues are 5, 5, and 5. So one eigenvalue of multiplicity 3. So then let's say I'm going to have to compute this matrix I minus lambda I in order to do eigenvalue eigenvector computations. And let's say this matrix here has rank equal to 2. I'm making this assumption. If it has rank equal to 2 and it has 3 columns, then that means it has nullity equal to 1, meaning the dimension of the null space is 1. That means that in solving this equation, A minus lambda I times Q equals 0, there's only one solution because the dimension of the null space is 1. So one solution for Q, meaning that there's only one eigenvector for this set of equations. And when I say solution for Q, it's really, remember, a vector solution that any linear multiple is also a solution. So it's not distinct numbers, but it's more of a direction. So the fact that I assumed this had rank 2 means it has nullity 1, which means there's only one distinct eigenvector. So in this video we're going to be talking about things called generalized eigenvectors. So to distinguish between generalized eigenvectors and eigenvectors, I'm going to keep using Q to mean eigenvectors, and I'm going to use V's to mean generalized eigenvectors. So let's say that in this case, this vector V, I'm going to call it V1, is equal to Q. So in this case, V1, a generalized eigenvector, is the eigenvector itself. So it's the solution. Okay? So that A times V1 is equal to lambda times V1. So I said that there was only one solution for Q, and this is it. So this is my one single eigenvector. So now, the interesting thing is there's going to exist some other vector, V2, where, because this is my only solution for my eigenvector equation, I know that if I take this other vector, V2, and I multiply it by this, it's not going to equal the 0 vector because it's not an eigenvector. But it's weird that there exists this other vector v2 that if I multiply it by a minus lambda I squared, that is equal to the 0 vector. So it's kind of this weird thing where it's this weird vector that doesn't meet the strict definition of what an eigenvector is, but if you take it and multiply it by this matrix and get that vector, and then multiply it by the matrix again, that thing is the 0 vector. I mean, that essentially means that this vector times this matrix must give you Q, because then that vector multiplied by the matrix is 0. So we call this thing a generalized eigenvector of grade 2, and the reason why it's grade 2, so let me just write that. V2 is a generalized eigenvector of grade 2. And what do we mean by grade 2? It's this squared is the reason why it's grade 2. Okay? It's that 2 that's making it grade 2. So by that definition, we could have gone back and said, what is V1? V1 is a generalized eigenvector of grade 1. But a generalized eigenvector of grade 1 is an eigenvector. So that's kind of interesting. So we have this weird vector V2 is going to exist that is a generalized eigenvector, but we're talking about 3 by 3 matrices here. So now we have this vector V1 and V2. Well, it turns out there's going to be another vector V3 such that if I take a minus lambda I squared times V3, that is not going to equal the 0 vector, but if I take a minus lambda I cubed V3, that is going to equal the 0 vector. So we call V3 a generalized eigenvector of grade 3, and this is the reason why it's grade 3. So now we have these 3 vectors that sort of, one is a true eigenvector, and the others, when I multiply them, keep multiplying them by my matrix, they start becoming eigenvectors. So we call those generalized eigenvectors, and the set of formulas that defines these vectors V2 and V3, which I've just until now told you exist, the formulas look like this. The formula for V1 was straightforward. It's the standard eigenvector eigenvalue formula. And the formula for V2 looks like this. A times V2 is not equal to lambda V2, but instead it's equal to V1 plus lambda V2. And when I take A times V3, that's equal to V2 plus lambda V3. So it's like these A V2 equals lambda V2 plus the vector before it. So it's almost like they all reference the generalized eigenvector equation for eigenvector 3 references back to equation 2. And only the generalized eigenvector 1 doesn't have to reference back to anything. So this is the set of governing equations, and it turns out that V1, V2, and V3 are linearly independent. So I can form this matrix V, which for its columns have V1 as the first column, V2 as the second column, V3 as the third column, like this, and V1, V2, and V3 are all linearly independent. So this matrix V is an invertible matrix, and it's also V1, V2, and V3 form a valid basis set because they're linearly independent. So it turns out now I can find, if I use this as a similarity transformation, I can take V inverse times A times V, because V is a valid basis set, so it represents a valid similarity transformation. And the thing I'm going to get is this matrix J. And unlike the matrix gamma for a diagonalizable matrix, where this was a diagonal matrix, this matrix J is a Jordan form matrix. And for the specific example I've just been working, that Jordan form matrix is going to look like this. Lambda, 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 0, 0, 0. And if this were a diagonal matrix, I would fill this with zeros as well. But this isn't a diagonal matrix, it's a Jordan form matrix. And a Jordan form matrix looks a lot like a diagonal matrix in that there's all of the lambdas on the diagonal and all zeros in the lower diagonal. But in a Jordan form matrix, the superdiagonal, which is the next diagonal row above the main diagonal, is all ones. So I fill the superdiagonal all with ones, and then I fill everything else with zeros. And in this case, everything else is just one more entry. But a Jordan form in general has eigenvalues on the main diagonal, ones on the superdiagonal, and then zeros everywhere else. And that is a Jordan form matrix. So, in fact, more specifically, we call this thing here a Jordan block of order 3. And what is a Jordan block? A Jordan block means each of the eigenvalues are the same eigenvalue as each other. So we're actually going to be able to make larger Jordan form matrices through small Jordan blocks. So this is a Jordan block of order 3, corresponding to our eigenvalue of multiplicity 3 that we started with. Now, what if instead of this preceding example, this matrix A minus lambda I was rank 1? Before we said it was rank 2. So if it were rank 1 and we have 3 columns, then that means, our nullity is equal to 2 in this case, since nullity plus rank equal number of columns. So if that would have been the case, and this matrix would have only been rank 1, our nullity would have been 2, and then this equation, A minus lambda I times Q equals 0, will have 2 solutions, right? Because our dimension of our null space is 2, which is our nullity. So there would have been 2 solutions to this equation, which means there are 2 eigenvalues. Or I should be more specific, 2 eigenvectors, 2 linearly independent eigenvectors that span this 2-dimensional space. So in that case, we know there are these 2 eigenvectors, Q1 and Q2, and for our generalized eigenvectors, we're just going to use those. So V1 is equal to Q1, and V2 is equal to Q2. But that means there's going to be this other V that exists, or V3 that exists, such that A minus lambda I times V3 is not equal to 0, but A minus lambda I squared V3 is equal to 0. So V3 is a generalized eigenvector of order 2. So, and then finally, the equation for V3 is that A times V3, it's not equal to lambda V3 because it's not an eigenvector, but it's equal to, V2 plus lambda V3. So it follows the same formula as before. And now our Jordan form matrix is not going to look like this. So we're going to compare to this. This was the 3x3 Jordan block that we got because of the last set of assumptions. But now we are going to get something that looks like this. When our Jordan block is solved by packing V inverse AV, we're going to get something that looks like this, where we have lambda, 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 0, 0, 0, but now it looks like 1, 0, 0. And it's because we actually have, inside of our Jordan form matrix, our Jordan form matrix is constituted by 2 different Jordan blocks. This is a 1x1 Jordan block, and it corresponding to V1. And then this thing here is a 2x2 Jordan block for V2 and V3. So, let's kind of parse what we're looking at here. First, do we believe these are all Jordan blocks? Do they meet the definition of a Jordan block? Okay, let's look at this one first. It has lambda on the diagonals, it has 1s on the superdiagonals, and 0s everywhere else. So this is a 2x2 Jordan block. Does this meet that? It's a 1x1 matrix, but it has lambda on the diagonals, 1 on the superdiagonals if the superdiagonal existed, and zeros everywhere else if anywhere else existed. So this is a 1 by 1 Jordan block. So we form a Jordan form matrix by a bunch of different Jordan blocks arranged on the diagonal. So you can sort of think of this Jordan block and this Jordan block being kind of on the main diagonal of this bigger 3 by 3 matrix, and then zeros everywhere else. And we have one Jordan block per distinct eigenvector. So in the first case, we only had one distinct eigenvector, so we had one big 3 by 3 Jordan block. In this case, we have two distinct eigenvectors, so we have two little Jordan blocks inside of the bigger 3 by 3 matrix. So when we did this, it could have just as easily been the case that that V1 was equal to Q1, and it was V3 that was equal to the second eigenvector. In that case, we would have ended up with something like this, where we would have had V2 as the generalized eigenvector, and it would have looked something like this. And so in that case, when we would have done our Jordan form, it would have ended up looking something like this: lambda, 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 0, 0, 0, 1, 0, 0. And our Jordan blocks would have been broken up like this. So this would have been the 2 by 2 Jordan block for V1 and V2. And this would have been a 1 by 1 Jordan block corresponding to V3. Because you see the relationship here is that V1 was a distinct eigenvector, and V3 is a distinct eigenvector, and it's V2 that is somehow tied to V1. In this first case, V1 and V2 were the distinct eigenvectors, and V3 was somehow tied back to V2 in its governing equation. So essentially what we're finding is it's the upper left entry of every Jordan block that corresponds to the generalized eigenvector. Or I should say the generalized eigenvectors that are actually eigenvectors. So here the upper left corner is the only one there is. Here the upper left corner is the number 2 entry in the matrix. In this case, the upper left entry is the number 1 entry, and the upper left entry of this Jordan block is the number 3 entry. So depending on which vectors are your generalized eigenvectors, you'll get a slightly different Jordan form. But this idea that you'll have a certain set of Jordan blocks based on the number of eigenvectors you have, you can know that in advance. So let's say that this matrix A minus lambda I has rank 0, which implies it has nullity 3, meaning its null space is a 3-dimensional space. And an example of a matrix like that is already a diagonal matrix of eigenvalues. Just if I take this thing, clearly its eigenvalues are lambda, lambda, and lambda, and if I subtract lambda I from A, then I'm just going to get a big 0 matrix. And a big 0 matrix is going to have rank 0. So this is the type of thing we're looking at in this case. So in this case, we're now back to this case of 3 linearly independent eigenvectors, because this is a diagonal matrix. So not only is it diagonalizable, meaning similar to a diagonal matrix, but it's trivially diagonalizable just using the identity matrix. So any diagonal matrix is of course diagonalizable, and the Q and Q inverse that you multiply it by are just the identity matrix. So the thing in the concept of Jordan blocks that's kind of interesting, though, is that this is also a Jordan form. A diagonal matrix is a Jordan form, and the way we break it up is like this. So a diagonal matrix is nothing more, a diagonal matrix, I should say, with eigenvalues of multiplicity greater than 1, is nothing more than a bunch of 1 by 1 Jordan blocks associated on the diagonal. So we now know that every matrix is similar to a Jordan form matrix, and in the case that a matrix is diagonalizable, it's also similar to a Jordan form matrix, and that Jordan form matrix is all 1 by 1 Jordan blocks. we have one Jordan block per distinct eigenvector, but the arrangement of those Jordan blocks is subject to decisions that you make. So let's work out another example. Let's say A is a 4 by 4 matrix. And let's say it has one eigenvalue lambda with multiplicity 4. So if A minus lambda I is rank 3, then we know it's nullity 1 and there's one eigenvector associated with it. So A minus lambda I times Q equals 0 has one solution because the nullity is 1. So the Jordan form, I already know in advance, is going to look like this. Without doing any work, just from seeing this, I can tell the Jordan form is going to look something like this. Lambda, 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 1, 1, 1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0. Because I only have one eigenvector, so I only have one big Jordan block. And this is how a Jordan block is described. Okay, now let's say instead, let's divide this page. Let's say instead A minus lambda I has rank 2. This implies nullity 2, which implies that our dimension of our null space for this equation, A minus lambda I times Q equals 0, has two linearly independent solutions. So there are two distinct eigenvectors. Well, that means our big A matrix has two distinct Jordan forms. Or excuse me, our Jordan form has two distinct Jordan blocks. But it turns out there's two different ways that we can have two Jordan blocks. So here's what we know in advance without doing any other math. Just by looking at this A minus lambda I matrix and looking at its rank, finding its 2, we know our Jordan form that we're similar to is of one of two forms. It might look like this. It's got to have two Jordan blocks. So basically, the two Jordan blocks could be like this, where I have a Jordan block here and a Jordan block here. And then these are all zeros. Or one or the other, we don't know which. Or it could be something like this, where I have a Jordan block here and a Jordan block here, and then zeros everywhere else. And then I could have also had a situation where this 1 by 1 Jordan block was up here and the 3 by 1 Jordan block was down here, but let's not worry about that because that's just a renaming of what we call V1 versus what we call V2. So basically the important thing is there's going to be two different Jordan forms, and I don't know which one it is yet. Only by looking at the rank of this, I don't know which one of these Jordan forms I have, but I know it's one of them because I know I have two distinct eigenvectors, which means my Jordan form has two Jordan blocks. I just don't know if it's a 2 by 2 and a 2 by 2 or a 3 by 3 and a 1 by 1. So it's going to be one of these two things. And let's not get hung up on this ordering here. So what if A minus lambda I has rank equal to 1? Well, if it has rank equal to 1, and this has 4 columns, then I know my nullity is equal to 3, meaning I have 3 distinct eigenvectors, which means I have to have 3 Jordan blocks. So my Jordan form is going to look something like this. If I need 3 blocks, one way I could make it is like this. Lambda 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So I have 3 distinct Jordan blocks, a 2 by 2, a 1 by 1, and a 1 by 1. Now again, this could be reordered. So this big 2 by 2 Jordan block could be the Jordan block in the middle, or it could be the third one. But that again doesn't really matter because it's just a naming of which of the which of the eigenvectors I call 1 and which one I call 2. We'll move these around. But the fact that it has these Jordan blocks, I know just by looking at the rank of this matrix. Finally, in this case, if A minus lambda I is rank 0, which would be the case if A were just that big diagonal matrix of lambdas, then I know I have 4 distinct eigenvalues because my nullity is 4. And in that case, my Jordan form is simply the diagonal matrix. The big diagonal matrix, if this is rank 0. So, to summarize, every matrix has a Jordan form that it's similar to, and similar means that there exists some matrix V that also has an inverse, V inverse, and if I do that similarity transformation, I will be similar to this matrix called a Jordan form. That Jordan form matrix consists of only Jordan blocks on its diagonal and zeros everywhere else, and a Jordan block has a very specific form, having all similar eigenvalues on its main diagonal, ones on its super diagonal, and zeros everywhere else. And I have exactly one Jordan block for every distinct eigenvector of A. This is going to be an extremely powerful and useful result for us in state space controls, and we are going to extensively use it to analyze the time domain solutions of state space formulations. So it's very important that we thoroughly understand the Jordan form.